You can start, Gerhard, please.
There we go. I was a bit muted. So my talk today will relate to model reduction of functions of matrices, basically. So we're going to look at the standard POD-DEIM algorithm. So anyone working on model reduction of standard vector type of functions will know about this. And we look at how it can be extended to functions of matrices into spatial dimensions. So this is work together with my supervisor, Valeria Simoncini. So to start off, we're looking at this function f, which is evaluated at the entries of a matrix, also time dependent, and the output is once again a matrix. The matrix U at which it is evaluated is also time dependent. And we want to see if we can approximate this function f in time using much smaller matrices so that we don't have to evaluate at each time step this function at a very big matrix. So what people have been doing in the past is they would consider a function boldface f, which evaluates a very long vector of length nx times ny, which we call the vectorization of this matrix U. So what this operator does, it stacks all the columns of the matrix U beneath each other. And if we then use this function f to evaluate at the entries of this vector U, we can say that this function is the vectorization of the matrix function. So I tell you this because I will first review what the standard methods are to reduce the order of this model, and then I will show how we can extend it to the matrix case. So let me just first show a motivational problem why we are considering this. So we're looking at a matrix valued ordinary differential equation, which has got this linear Sylvester term, some constant term, and this nonlinear matrix function. This commonly comes from a discretization of a PDE of this form. It's got a linear, probably diffusion operator here, a nonlinear term, and a forcing term. And this PDE is in 2 dimensions. So in the paper that in the article that we wrote, we were looking at this entire equation and how to form a reduced order model of that. But today we'll only focus on the term f of u comma t. So of course, the application of this type of equations is very wide, biology, ecology, virology, and it continues because it's basically anything that studies and controls the time evolution of some complex phenomena. So if we now take this nx times ny term and we denote it by capital N, we will see we want to approximate this vector function by the discrete empirical interpolation method. So this was introduced originally by Chatterantabut and Sorensen in 2010, and it's based on the empirical interpolation method by Baralt et al. From 2004. So to approximate this function at all time instances, we consider a very tall matrix VP of a dimension P, where P is much smaller than big N. And we want to approximate F as a linear combination of the columns of this matrix VP. And the coefficients for this linear combination is contained in the short-ish vector relative to N, C of T. And the column of the matrix VP is an orthonormal basis of some subspace that we will discuss in a little while. So to determine this coefficient in the vector C, they define this matrix P, which is a subset of columns of the identity matrix, P columns to be exact, at some interpolation indices. So this matrix P is then used to select small p rows from both sides of this equation. So we get this equality, and then solving for the coefficient vector C of T, we get this approximation of the function f. So we see that's this oblique projector from the left multiplied with the original function f, and the coefficient vector c of t is this term here. Of course, c of t is now in Rp, which is much smaller than n, but the function f is still evaluated at all the entries of the long vector u. But since we assumed that the function f is evaluated element-wise at the entries of u, we can take the p inside here and just evaluate it at this selected rows. So it's just, you're evaluating the function at just p entries instead of big N. So what remains to be done is how to determine this orthonormal basis and how to select the interpolation indices. So we first look at the orthonormal basis, which is done by the proper orthogonal decomposition, or POD. So for those who are not familiar, just a short overview, the proper orthogonal decomposition collects what we call snapshots of the function f. So if uj is u evaluated at time tj, and fuj tj is denoted by fj, we consider ns snapshots. So it's basically data evaluated at all these different time instances, and we collect them into a typically tall matrix. Normally ns is smaller than capital N. And we call this matrix S, and calligraphic S is the space range S, so the space of snapshots. So what the proper orthogonal decomposition does is it determines VP as the best rank P approximation of the space S. Or for us in linear algebra, another nice way to say the truncated SVD. So as simple as that, we can collect the snapshots into this matrix. We take the SVD and truncate it so that VP contains the first P left singular vectors. Sigma P is the top P by P block of the singular value matrix, and WP also contains the first P right singular vectors. And if we denote this by SP, we have this error S minus SP is sigma P plus 1, which is the P plus 1 singular value, which is, I think, a well-known result. So to do the model reduction in vector form, as I said, the first step now is to determine the basis matrix VP by the proper orthogonal decomposition, given these snapshots Fj. Of course, drawback number one is that this matrix has length n, and you're storing ns vectors of length n, and also doing a SVD of this very large matrix. So this is computationally and memory-wise very demanding. And also taking the matrix functions, vectorizing it, and taking an SVD destroys a lot of symmetries and other properties that are actually shown in the original matrix functions. Next, to determine the interpolation indices, I won't go into detail, but given this matrix VP, in the original paper by Chatterantabut and Sorensen, they use a greedy method based on the minimizing the residual to determine the interpolation indices. And then recently, Denmark and Gugerson have shown that it can also be done by taking a pivoted QR factorization of the matrix VP transposed. Either way, both of these have an order capital N operation count, which is also rather expensive depending on the size N. So we were thinking one way to approach all these drawbacks is why not look and apply a similar procedure directly to the matrix functions F without having to vectorize. So we assume now that this function evaluated at the entries of the matrix is well approximated by low rank for all time t. And we consider without loss of generality that we're now dealing with square matrices of dimension n. It can, of course, be extended easily to the other setting. So we considered two tall matrices and with orthonormal columns, VL and WR, and of dimension P1 and P2, where both P1 and P2 are much less than n. So we approximate this function f with this low rank product where VL is tall and skinny, C of T containing the coefficients is a very small matrix, and WR transpose is fat. So we want to approximate F in all time, in the entire time span with this low rank product with only the coefficient matrix C of T changing. So as we did before with the standard DEIM, we define these matrices PL and PR now, two matrices, one from the left and one from the right, also containing respectively P1 and P2 columns of the identity matrix. So same as before, we select P1 rows on the left, we select P2 columns from the right and solve for this matrix C of T, and we obtain the following approximation of the function f of u. So the coefficient matrix here, C of T, is this part, and there we see the two basis matrices, as I'll call them. So C of T is small and has size P1 by P2, but still we see that this function f is first evaluated at all the entries of u, n by n, and then only projected, as I can say. But since f is evaluated at the entries of u element-wise, we can take the p's inside, and we're only evaluating at P1 by P2 terms. So the remaining challenges now are how to determine these matrices, VL and WR, so that they approximate well the space of snapshots in the entire time span. And that's where we introduce the two-sided POD, and also then how to determine the interpolation indices containing PL and PR. So first we look now at a two-sided proper orthogonal decomposition. So this time we consider a set of matrix snapshots, F evaluated at Uj, where Uj is U of Tj, and Tj is denoted by Fj. So each of these has size n by n, and we collect a set of them. And we use these snapshots to determine a space on the left and on the right, which approximates well the space of all the snapshots. So firstly, we can interpret the snapshots as an unfolded third order tensor. So we have this first mode and second mode unfolding, which this one is very fat and this one is very tall. Theoretically, what one can do is go and take the SVD of this one and take the SVD of this one. And it's easy to see that you will have an orthonormal matrix on the left-hand side here and an orthonormal matrix on the right-hand side here, each of size n by n, which in fact approximates the space of all snapshots. One which can also be truncated, which is what we're after, but no one wants to go and do a SVD of matrices of this size, and especially if n is very large and also if there are a lot of snapshots, ns. So we had to get more creative and think of a way in which we can approximate this space of snapshots without having to do the SVD of these large matrices. So in very short, the efficient algorithm that we decided on is to loop through all the snapshots one at a time. So consider snapshot Fj, and then we will take the sparse iterative SVD of this snapshot and just determine the leading gamma singular values and vectors and approximate Fj with this very low rank product. And we've, in our experiments, seen that very few singular values and vectors are necessary, maybe 3 or 4 even of each snapshot. So once we've done that, we can actually discard the snapshot Fj, throw it away, and just keep this information. So all the Vj's, all the left singular vectors of each snapshot are kept together in this matrix, and all the right singular vectors transposed are kept together in this matrix. And what we then do is the user can also select that these, these matrices can have a dimension of maximum kappa, for example. So what happens then is after iteration j, if the dimension is greater than kappa, it reorders all the previous singular values and in comparing the singular values to each other, we truncate the first kappa left and right singular vectors. So that means that not the same amount of information from each snapshot will be kept, but only the most important information relative to all other snapshots. So we keep the kappa most important left and right singular vectors by comparing all the snapshots to each other. What we show then is if we take the SVD of these two matrices that we collected, and we have the left singular vectors of this one here and the right singular vectors of this one here, we show that all snapshots can be written as a linear combination of these two matrices. So in a very cheap way, we've determined our left and our right orthogonal matrices that, approximate well the space of all the snapshots. Of course, then, if the singular values contained in these matrices S bar and S hat have rapidly decaying values, this space can be even further truncated to have a low rank approximation of all singular values, of all snapshots in time. More importantly, we've also shown that if all snapshots are symmetric in the time span, that we only need this one matrix V used from the left and right, and we retain the symmetry of the original snapshots by this approximation. Okay, so in summary of the two-sided method, we use this two-sided POD algorithm to determine the basis matrices VL and VWR given the snapshots Fj, and which means we're only storing vectors of length n and only doing SVD with vectors of length n, where n is now square root of big N, which is a big gain in terms of memory and computational time. And as we've shown, symmetries and other structures of the matrices can actually be retained. Furthermore, to determine the interpolation indices, either the greedy method from Chaturanthabut and Sorensen or the QR method from Dirmak and Gugerson can be applied independently to this one on the left and to this one on the right. So there's no extra complexities in determining the interpolation indices, which now only has order n operation counts since these matrices have length n. So then I will show just one quick example. So we consider this scalar function f of u, where which is 1 over square root u plus 0.1 squared. And we consider it for two different functions u in the space domain 0, 1, 0, 1. And the first function is a very symmetric one where the movement in the x and y direction is the same. And the second is one where the dominant movement is in the y direction and almost no movement in the x direction. So for both functions, we discretize with 700 nodes. So we're dealing with matrices of size 700 by 700, and which is 490,000 entries in total that need to be dealt with. And we consider 150 snapshots in the time span. Also, to evaluate the error in the approximation, we considered 25 time instances which was not in the snapshot set, and we average the error in these at these time indices. So just to show you the two functions on the grid. So the first one I said is more symmetric. It starts here in the corner and it ends here in the middle. And here we see how the peak has moved. So we see the movement in the x and the y direction is about the same. Where for the second function, it starts here on the left and ends in the middle, and we see the peak has moved directly only in the y direction. The reason we show this is we want to show how the two-sided approximation can take advantage of preferred spatial marching directions of the functions. So what we plot here is the dimension of the left approximation space, P1, so the dimension of the matrix VL, and the dimension of the right approximation space, P2, the size of the dimension of the matrix WR, and then the average relative error. So on the left, we have the function f of u1, and we actually see the quickest way to let the error decay is to just select P1 equal to P2 and go down, where, which agrees with the theorem that we showed earlier, that we can use the same approximation space from the left and the right if the functions are symmetric, or the snapshots. So, and here we see P120, P220, for example, already gives an error of 10 to the minus 5 in comparison to the original 700 by 700 matrix. For the second function, where most of the movement was only in the y direction, we see that the left side of the left approximation space, the error decays almost immediately. So we can consider an approximation space of dimension 2, for example, and increase the dimension of the right approximation space to 20. So we have 2 on the left, 20 on the right, and get an error of 10 to the minus 5. So this shows the advantage of how the two-sided method can reveal more preferred spatial marching directions and consider less information on one side than the other, perhaps. And just quickly to show a time comparison to the standard vectorization method, which we indicate by PD, and ours is two-sided PD. And we consider two sizes of the matrices, or number of discretization nodes in each direction, 1,000 and 2,000. We see to get the SVD to determine the basis, the timings are still comparable for n equals to 1,000, but as soon as you start going larger, you see the big advantage in terms of just computational time to get the basis. And then if you look at memory as well, we store 800 vectors of length n, so of length 2,000, where vectorization would require storing about 400 vectors of length 4 million. So there you see the advantage in terms of memory as well. Okay, so in short, to conclude, we see that we require for our method no mapping to R big N, a dramatic decrease in memory and CPU time, and that the symmetry and preferred spatial marching directions can be taken advantage of. We want to extend this to perhaps 3-dimensional or higher dimensional spatial problems with a tensor POD-DEIM method, and look at parameter dependent problems. And this was very brief. So if you want to look in more detail or have any questions, there is the related article, and feel free to ask me any questions otherwise.
Thank you, Gerhard. I think we kind of ran out of time. And please, if you have any question, join us on Gather to ask questions to Gerhard. I would like by now